Hello learners, today we are going to discuss chemical kinetics. After going through this, you will be able to understand the rate of reaction, explain the average and instantaneous rate of a reaction, express the rate of a reaction in terms of change in concentration of either the reactants or products with time. The three main aspects related to study of reactions are, first being spontaneity of a reaction based on Gibbs free energy change, that is, delta G equals negative, reaction is feasible, and if delta G equals positive, reaction is not feasible. The second aspect being extent to which the reaction takes place before equilibrium is achieved. And the third and the most important aspect is the time taken for completion of reaction, that is rate or speed of a reaction. In our daily lives, we see various chemical reactions taking place. Let's perform some reactions and note the speed at which it is taking place. We are going to react potassium iodide solution with lead acetate solution. Carefully observe the change in color. A yellow precipitate is formed. Formation of precipitate shows that reaction has taken place. How much time did the precipitate take to appear? It took few seconds for the precipitate to appear. This is an example of reaction proceeding at fast rate. Activity 2, in which we will see the reaction between copper sulphate solution with zinc granules. We will take copper sulphate solution in a beaker and add zinc granules to it. Can you see any change? No. Let's wait for some time. Now can you see any change? Yes. The blue color of copper sulphate has started disappearing and the solution is becoming gradually colorless. Such type of reactions are said to proceed at moderate rate and take time for completion. Let's take another example to understand another type of chemical reaction. If we look at an iron nail which is new, it has a shiny metal surface, whereas an iron nail which was kept in open air for some time has a brown coating on it. This is due to rusting of iron, which is an example of slow reaction. This type of reaction takes months and years to complete and proceed at a very slow rate. Have you ever wondered why some reactions are slow and some are fast? We get the answer of this query by studying chemical kinetics, which deals with the reaction rates and also explains why certain reactions are fast and others are not. It also describes the conditions which affect the rate of a reaction. Let us try to understand what is rate of a chemical reaction. Just think about speed of an automobile. You know that it is expressed in terms of change in the position or distance covered by it in a certain period of time. Similarly, can we understand the rate of chemical reaction as the change in concentration of a reactant or product in unit time? Let us consider a hypothetical reaction, reactant A forming product B. Here, 1 mole of the reactant A produces 1 mole of the product B. If A1 and B1 are the concentrations of reactant and product respectively at time T1, A2 and B2 are the concentrations of reactant and product respectively at time T2. Then rate of reaction can be represented as decrease in concentration of reactant with time, that is R equals to minus delta concentration of A upon delta T, where minus delta A is equal to concentration of A2 minus concentration of A1 or increase in concentration of product with time, R equals to plus change in concentration of B divided by change in time, plus delta B equals to concentration of B2 minus concentration of B1, and delta T is equal to T2 minus T1. The square brackets in these equations are used to express molar concentration. Hence, we can say that rate of disappearance of reactant A is decrease in concentration of A with time, which will be represented with negative sign, or rate of appearance of product B is increase in concentration of B with time. Since delta A is a negative quantity, it is multiplied by -1 to make the rate of reaction a positive quantity. The equations shown here are called average rate of reaction, which depends upon the change in concentration of reactants or products and the time taken for that change to occur. Look at the reaction of mercury with chlorine, which leads to the formation of mercury chloride. In this reaction, stoichiometric coefficients of the reactants and products are same. Hence, rate of reaction is represented as shown here, that is minus delta Hg divided by delta T, or minus delta Cl2 divided by delta T, or delta HgCl2 divided by delta T. That is, rate of disappearance of mercury or chlorine is same as the rate of appearance of mercury chloride, but situation is not always like this in all reactions. Let us consider a reaction where stoichiometric coefficients of the reactants and products are different. Rate of consumption of Hi is twice the rate of formation of H2 or I2. Hence, to make them equal, the term delta Hi is divided by 2. Therefore, rate of reaction is expressed as shown on the slide. Do you think the reactions take place at the same rate from starting to end? No, the rate of reaction is different at different time. Hence, we calculate rate of reaction over an interval of time. It gives us average rate of reaction. Let us understand by taking this example. A moles of reactant R forms B moles of product P. Average rate is defined as the rate of change in concentrations of the reactants or products at a particular time interval. Here, average rate is decrease in concentration of R with time or increase in concentration of P with time, as you can see on the slide. Average rate equals to minus change in concentration of R divided by delta T multiplied by 1 upon A equals to change in concentration of P divided by delta T multiplied by 1 upon B, where delta represents large change, but average rate cannot be used to predict the rate of a reaction at a particular instant, as it would be constant for the time interval for which it is calculated. So, to express the rate at a particular moment of time, we determine instantaneous rate. Instantaneous rate is defined as the rate of change in concentration of any one of the reactants or products at a particular time. Hence, mathematically for a very small time dt, we may express instantaneous rate as R instantaneous equal to minus dr divided by dt multiplied by 1 upon A equals to dp upon dt multiplied by 1 upon B, where d represents infinitesimally small change. Rates can be determined graphically as well. If we plot the graph of concentration of reactant versus time, we get the graph as shown here. From the graph, we can see that concentration of reactant R decreases with time. To calculate the average rate of reaction between any two instants of time T1 and T2, the corresponding concentrations C1 and C2 are noted from the graph. Then we can calculate the average rate of reaction by substituting value of change in concentration, that is delta R and delta T. R average is equal to minus delta concentration of R divided by delta T equals to minus within bracket C2 minus C1 divided by within bracket T2 minus T1. And to calculate the instantaneous rate of reaction at a specific time t, a tangent is drawn to the curve at the point corresponding to that time. The slope of the tangent, that is dr by dt, expresses instantaneous rate of reaction. Similarly, we can calculate the average and instantaneous rates of reaction by plotting a graph between concentration of product versus time. Therefore, R average is equal to delta P divided by delta T. R instantaneous is equal to dP divided by dt, which is equal to slope. We know that unit of concentration is moles per liter and unit of time is second. Now, can you derive the unit of rate of reaction? Yes, you are right. It is moles per liter per second. We have arrived to the conclusion that rate of a chemical reaction is defined as the change in concentration of any one of the reactants or products per unit time. Rate of reaction can be measured in terms of change in concentration of reactants and products per unit time. We have also learned how to measure rate of reaction graphically by plotting graph of concentration of reactants and products with respect to time. Here are a few questions for you to practice. Question 1. What are the rates of production of nitrogen and hydrogen in decomposition of ammonia? Given the rate of reaction is 2.5 multiplied by 10 raised to the power minus 4 moles per liter per second. Question 2. Differentiate between average and instantaneous rate of reaction. Question 3. The decomposition of N2O5 in CCl4 at 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 moles per liter, and after 184 minutes, it is reduced to 2.08 moles per liter. The reaction takes place according to the equation 2N2O5 gives 4NO2 plus O2. Calculate the average rate of reaction. What is the rate of production of NO2 during this period? Now, we have discussed about general idea of a rate of a reaction. There are so many factors which affect rate of the reaction. We'll discuss about these in the next episode. Thank you. Stay safe and healthy.